Measles is a horrific, highly contagious viral disease that causes fever and red rash on the skin. This infectious disease is largely forgotten about in a lot of countries due to the impact that the measles, mumps, rubella vaccine had in 1989. Unfortunately, measles is abundant in many developing countries due to the lack of accessibility and mass population. Although rapidly dropping, one of those countries is India. In this analysis, I will be running diagnostics on a set of AREMA models fitted to the time series of measles cases in India from 1980 to 2018. The dataset I will be using for this analysis was subsetted from a large database of infectious disease from the World Health Organization. The data records a number of cases of each infectious disease for a large set of countries. The set that I will be using is the infectious disease measles in the country of India. The time series plot for India shows an unseasonal dataset with a slight quadratic decaying trend. There is an intervention point evident from the vertical dashed line at 1989, which marks the introduction of the famous MMR vaccine. After 1989, there is a clear behaviour of autoregressive and moving average points. The fluctuating variance is profound before this intervention point, but still exists post-1989. There is a strong positive linear shape in the correlation plot on the left, which also has a correlation value of 0.84. The ACF displays a clear decaying trend with 6 lags above the significant bounds, and the PACF shows 1 significant lag above the bound and the rest being contained within the bounds. The pattern in the ACF proves that there is a trend in the data. Due to the characteristics spoken in this slide, I will conclude that the data is non-stationary. The Box-Cox plot above has produced a lambda value of around 0.5, which suggests a square root transformation. Applying a square root transformation on the data has developed a more normally distributed series. Visually, this can be seen in the QQ plot with most of the data points lying on the line. The p-value in the Shapiro test is smaller than the significant value, which means the data isn't normally distributed, but it is certainly more normal than the original series. After applying the first difference on the data, we can see that the decaying trend has been eliminated, evident by the even distribution of points above and below the line placed at the mean of 0. I can still see the intervention point, but it is less obvious than the original dataset. Both of the ACF and the PACF of the first difference has no significant lags outside the bounds, which is leading me to believe that the stochastic component of the difference data is white noise. I'm going to continue with model parameter specification as I'm convinced that the data is stationary and appropriate. As seen in the previous slide, there were no significant lags in the ACF and PACF plots, so I've used the extended autocorrelation function and BRC tables to derive tentative P and Q values. For the first procedure, the EACF has a dividing vertex at 0, 0, which gives us tentative models AREMA 011 and AREMA 111. Secondly, the BRC table has shaded regions at P equals 2, 3, and 4, and Q equals 1, 4, and 6. The BRC table produces some large models, so by the principle of parsimony, I will choose 6 smaller models. These models are AREMA 011, 012, 211, 214, 311, and 314. If I can't find a good model from this set, I will backtrack and run diagnostics on the bigger models. Using the coefficient test for maximum likelihood estimation and least squares estimate process, the model which had significant coefficients in both estimates was the AREMA 011 model. This model had a significant MA1 process with the least squares coefficient negative 0.33 and maximum likelihood coefficient negative 0.35. The BIC and AIC tables both work in favour of the AREMA 011 model, with the AIC equals 411 and BIC equals 414. Going forward, I'll do a residual analysis on this model. The time series plot of the residuals for AREMA 011 model have an even scatter above and below the line placed at the mean of 0. This tells us that the correlations are independent and could be normally distributed. The ACF and PACF plot contains all lags within the bounds. To rectify even further, looking at the QQ plot, I can see that most of the data points lie on the QQ line, with only slight perturbations at the tails, meaning the data could be normally distributed. The Shapiro-Wilk test has a large p-value, meaning there is not enough evidence to reject the null hypothesis of normality. The box Pierce and box lung test both have large p-values, meaning we do not have enough evidence to reject the null hypothesis that the errors of the residuals are uncorrelated. On the left is the forecast plot of the original data. The blue line is a constant value of 17,702, which is a deviation of 1,772 from the last point recorded in 2018. The blue area of the forecast represents 80% confidence interval, and the grey area represents a 95% confidence interval. Without any huge eradications, the ARIMA 011 model says that the cases of measles will continue to be detrimental if no action is taken. On the right is the same model applied to the subset of data after the MMR vaccine. The forecast is similar, but has large confidence bounds than the previous. The forecasted values for both the original dataset and the reduced series shows similar values for the next 10 years. As you can see in the left table, the forecast is 17,702, and in the right table, the forecast is 17,647, giving a variance of 55 cases between the two series. In this analysis, I developed a detailed knowledge of the trends that exist in measles cases, specifically in India. One thing that stood out to me was the impact that vaccination had on the number of cases of measles in particular countries. It is clear to see that the introduction of the MMR vaccine in 1989 had an astronomical impact on the measles cases, allowing it to drop from 165,771 cases in 1989 to 19,474 cases in 2018. That is a huge drop of 146,297 cases over 28 years. Through rigorous analysis, I found that the best model to fit the data was the ARIMA 011 model, which provided a pleasing forecast for the next 10 years. With more analytical skill and knowledge in time series analysis, I would be curious to try and model the pulse interventions in the time series plot for the cases in Bangladesh, as seen on this slide. Thank you.